Now let us solve a transportation problem. For example, we are given three sources, A, B, and C, and four destinations, W, X, Y, and Z. For sources A, B, and C, the supply for them is 300, 400, and 500 respectively. The destinations, W, X, Y, and Z, have demands of 250, 350, 400, and 200 respectively. To begin with, we must perform the northwest corner rule. This rule states that the allocation of resources starts at the upper left corner of the table. To do this, the quantity of the supplies must first satisfy the quantity of the demand for the designated row or column. If it is inadequate, the succeeding row of supply will then tend to the demand until the demand has been satisfied. The process repeats until every demand has been accounted for, generating your feasible table rather. So to begin with, we start with cell AW because it is our most northwest or our upper leftmost cell. So source will provide its supplies to destination W, the demands of destination W. Hence why we will provide 250 supplies to adequately satisfy the allocation of resources for the demands of column W. So the cell AW is 250. Now, as you can see, we are left with 50 supplies left, but the demand for column W has been satisfied. So we move to the demand for column X. So source A will then move its remaining supplies to column X. Now, we have reduced the demand for column X by 50, and we are now left with 0 supplies for source A. As per the rule, we move down to the succeeding rows, so source B will now tend to the remaining demands. As you can see, source B is able to allocate enough supplies for the demands for column X. Hence why it is now 0. It is left with 100 supplies left and will now tend to the demands of column Y. Now that source B is finished, we move to our final source, which is C, which will now tend to the remaining demands. So source C is able to supply the demand for column Y and will most definitely supply the demands for column Z. This is now a feasible table in which we will then perform our optimality test. So to begin with, we must perform now the stepping stone method. So we select an unused square, any unused square, to be evaluated. Then with this square as a starting point, trace a closed path with surrounding squares that have been used until you return to the starting point. Squares that have not been used will be skipped or set over. After which, in an alternating fashion, assign each square with a plus and minus sign, with the starting point having a plus sign. By squares that have not been used, we mean that squares that have no values. So we have cell AY, cell AZ, BZ, cell BW, CW, and CX. Now I chose cell AY to begin with. Cell AY can move to cell AX or cell BY. It cannot go to cell AZ because AZ has no value. Furthermore, cell AY cannot go to cell BX because AY cannot go diagonally. You cannot go to squares that are diagonal to you. Same can be said to cell AY to cell BZ. Let's begin. So for this case, we started from cell AY to cell BY, downwards, then to BX, to the left, AX, to the top, then back to AY. Now as you can see, we would then designate a plus or minus sign to each square in an alternating fashion with the origin having a plus sign. So since AY is our origin cell, 7 will now have a plus sign, 5 will now have a minus sign, -5. Then alternately, 6 will have a positive, 1 will have a negative. Then we simply add these values. So we have 7 minus 5 is 2, 2 plus 6 is 8, 8 minus 1 is 7. This is now your improvement index. Now do note that if the value is greater than or equal to 0, then it is a plausible value. If the value is negative, then the cell is unoptimized. Since our improvement index is positive, cell AY is a plausible value in which we will not, for this matter, perform any optimality test for this specific cell, in which we will discuss in the upcoming slides. Next, we move to cell AZ. Now here's where it gets complicated because cell AZ has no surrounding squares in which we can go to. Again, we cannot go from cell AZ to cell BY. We cannot go diagonally. So what we do is we skip over cell AY and move to cell AX. Then we trace a closed path with the squares with values until we return to origin point. For example, in this case, we can go from cell AZ to cell AX, which I did, or we can also go from cell AZ to cell CZ, which it has no difference. For this case, we went from cell AZ to AX, then down to BX, BY, CY, CZ, and back to AZ. Again, assign the plus and minus signs. So plus, negative, plus negative, plus, minus, negative, plus. Then we add once again. 4 minus 1 is 3, plus 6 is 9, minus 5 is 4, plus 3 is 7, minus 2 is 5. Our improvement index is a positive, henceforth it is a plausible cell. Now let us move on to cell BW. Can you solve for it? We can either go from cell BW to AW or BX. Either way is okay. For this case, we went from BW to BX. So again, assign the plus and negative sign. So we have a 2 minus 6 is negative 4, plus 1 is negative 3, minus 3 is negative 6. As you can see, our improvement index has a negative, in which case we'll perform an improvement of such index, in which we will discuss later. However, before we start to check on this, improve on this index, we must first solve for the other squares to determine if cell BW is indeed the lowest value. Okay, let us first solve for cell BZ, CW, and CXX. Now for cell BZ, again surrounding squares. So we have a 9 minus 5 is 4, plus 3 is 7, minus 2 is 5. So BZ, BY, CY, CZ, BZ. Cell BZ is plausible. It has a positive improvement index. Let's go to cell CW. CW, once again, same problem with cell AZ, where it has no surrounding squares with values, so we hop. In this case, I went from cell CZ, hopped over W, and moved on straight to AW. CW rather, to AW. So now we have a sign again in an alternate fashion. So this is positive, negative, positive, negative, positive, negative, and back. Let's begin. So 8 minus 3 is 5, plus 1 is 6, minus 6 is 0, plus 5 is 5, minus 3 is 2, and cell CW has the positive improvement index. Finally, let's move to cell CX. Cell CX, we go from CX to BX, to BY, to CY, back to CX. So 3 minus 6 is negative 3, negative 3 plus 5 is 2, positive 2, minus 3 is negative 1. So as you can see, we have two negative indices now, cell BW and cell CX. Now as you can see, cell BW is lower than cell CX, hence why we will tend to cell BW first. Now look at step 2a. If the value is negative, then the cell is unoptimized. To solve this, Find the smallest value in all squares with negative signs. Then, subtract this value from the other negative squares, whilst adding it to those with the positive values. So to make this simpler, let's move the other cells out of the way and focus first on cell BW. So as you can see, we assign these values as, we assign these, again, the positive and negative sign. However, we find for the smallest number in the cells with the negative sign. So we have AW and BX, since these cells have negative signs. Which among the two are smaller? Most definitely cell AW. So what the rule states is that we subtract this value from the other negative squares. So we have 250 minus 250 is 0. 250, 300 minus 250 is 50. But for the positive squares, we simply add them. So 0 plus 250 is 250. 50 plus 250 is 300. As so. Next, we move on to cell CX, since it has a negative index as well. So again, we assign the positive and negative sign. Among these two squares with the negative signs, 50 is lower than 300. That's why we will deduct 300, 50 from 300, while adding 50 to these two cells. So 50 minus 50 is 0, 300 minus 50 is 250, 0 plus 50 is 50, 100 plus 50 is 150. As so. Now let us perform again back to step 2, which is to check for the optimality test. Start again. So AW to AX to CX to CY, BY, BW, back to AW. Again, positive, negative, positive, negative, positive, negative, positive. So we have 3 minus 1 is 2, 2 plus 3 is 5, 5 minus 3 is 2, plus 5 is 7, plus 2 is 5. The same process repeats for all the cells, cell AW, cell BX, cell CW, cell AY, and cell AZ. The reason why we did not calculate for the improvement index for cell BZ is because cell BZ has remained the same despite the changes in the table. Remember, cell BZ, we went from BZ to BY, CY to CZ. These squares remain the same, so henceforth, there will be no changes for cell BZ. And that is how we know that cell BZ still remains a positive index. Congratulations, your optimal table has now been identified. But to ensure that this is indeed a correct table, we can do a checking first. To do this, we must add the values present within the same row or column and ensure that it is equal to the supply and demand. So for column W, we have 250 on it, and it is equal to the demand of column W. For example, let's go to row A. Row A only has 300, which is equal to the supply of 200, so that's good. So for cell BW, let's look for the source B, for example. So 250 plus 150 is 400. So now we know that this is correct. Let's move on to column X. 300 plus 350. 300 plus 50 is 350. So this is correct. 150 plus 250 is 400. That is correct. And finally, 200. Let's check again for source C. 50 plus 250 is 300. Plus 200 is 500. So now we know that this table is indeed correct. Now, once the optimal table has been achieved, calculate the overall cost by multiplying the values to the given cost of transportation present in each chart. For example, we multiply cell AX, which is 300 is transportation cost. Same goes for cell BW, 250 times 2, 150 times 5, 50 times 3, 250 times 3, 200 times 2, and we get 2,850. But let's compare to our feasible table that we got last time. Again, 250 times 3, 50 times 1, 300 times 6, 100 times 5, 300 times 3, and 200 times 2, we get 4,400. Now that is a big difference. How big do you ask? Well, 4,400 minus 2,850 is 1,150. So we save 1,150 currency. So that is why transportation problem is very useful in optimizing and minimizing costs. Thank you.